Well, greetings from the American Segmental Bridge Institute. We're ready to start the May webinar. I'm Greg Freeby, the Executive Director of the American Segmental Bridge Institute, and I want to welcome you all again to the webinar today. If you're not already following me and the American Segmental Bridge Institute on LinkedIn, I'd encourage you to do so. Certainly you can visit our website and find out about upcoming events and things, but LinkedIn is another good place to get more up-to-date information on things that we're doing at the American Segmental Bridge Institute. Hopefully you are all here today to see Jacob Rausch's presentation on fabrication of the Blue Ridge Parkway segmental bridges, and Jacob is going to be doing that from a precaster's perspective. So it's certainly a unique opportunity for us to have a precaster joining us. Some quick announcements just so that everybody's on the same page. Our monthly webinars are typically the last Wednesday of the month. We've done a single sign up this year. There's a QR code here on screen. There's also a link to this under the webinars section of our webpage. You can go to this. We simply ask for your first name, last name, and email address. You'll get an email then each month prior to the monthly webinar with an opportunity to add that as a calendar appointment. You'll know what the topic is and be able to make a decision about attending or not, but certainly we encourage you to attend. We think we have a really broad range of great topics each month. It's a great opportunity for everybody then to learn a little more about segmental and complex concrete structures. Wanted to do a little plug for the resource guide for concrete bridge design and construction. This was a collaborative document published by AASHTO and the National Concrete Bridge Council, for which the American Segmental Bridge Institute is a member. This QR code will take you directly to that publication. It's a free download. It's a great catalog of all of the resources for concrete bridge design and construction, organized by the various industry institutes that have those opportunities, both documents, training, certifications. It's sort of a one-stop shop. So I encourage you to find that publication if you haven't seen it already. Our June webinar will be on Wednesday, June 25th, also at noon Central Time. Mr. Kent Montgomery with GM2 Associates, who's been writing a series of articles in Aspire Bridge Magazine, if you subscribe to it. Kent will be talking about preliminary design approximations for segmental bridges. So great opportunity to learn a little bit from one of our industry titans. Some instructions on the webinar. If you lose your connection, you can rejoin with the link that we sent you. Certificates for attendance of the webinar will be issued about a week after the webinar. We have to go through and verify that everybody attended at least 45 minutes of the webinar. And again, just give about a week to receive that certificate. If you haven't seen it, then you can certainly reach out to us. We will be doing a live Q&A at the end of the presentation. You can access that through your desktop, through the dialogue and GoToWebinar. You have a little questions click. You can click that and then type in your questions, and then we'll hold those till the end of the presentation, and then we'll do a live Q&A session at the end. If you're on a mobile device, you can also type in questions. You have a little question mark in the upper right-hand corner that you can use to access that questions pane. I mentioned we'd be doing a live Q&A. Wade Bonzen, who's the chair of the ASBI Construction Practices Work Group, will be leading that discussion. Wade is a project development manager for complex bridges at GM2 Associates, and you'll be hearing then from Wade just a little bit later. So I want to introduce our speaker today, and then I will turn over. Our speaker today is Jacob Rausch. He's a precast concrete engineer at Coastal Precast Systems in Wilmington, North Carolina. He received a bachelor's and master's degree in civil engineering from Penn State University. And after graduation, he worked in the design office at Fig Engineering and then worked in the casting yard for the Klein Avenue Bridge. He's been involved in a number of projects, but to date, he's been involved in the precasting of 3 independent or separate segmental bridges. So he brings a unique perspective on precast segmental bridges, that of sort of from the fabricator's viewpoint, which is why I invited him to present today, because I think he does have some unique knowledge. You'll also find in the handouts, the click that you have, and I know Jake will mention this also later, you'll find there's a handouts click that will bring you to a Aspire article that Jake wrote on this very topic. So there's some additional learning, additional reading opportunities if you want to do that. So with that, I will turn it over to Jake.
All right, great. Can you see my screen?
Sure can, and we can hear you just fine. So thank you.
All right, perfect. Thank you. All right, so as Greg mentioned, I'm going to be talking about the Blue Ridge Parkway segmental bridges. And last spring, Justin Campbell and Jan Zitney had presented a webinar on these 2 bridges. They had kind of focused more on the erection design side. So I'm going to focus on the fabrication of those precast segments. And then it's just at the end, you'll have an understanding of the segment fabrication process, how certain design and detailing choices impact segment fabrication, and segment delivery in landlocked locations. So as it was mentioned, the segments were precast at Coastal Precast Systems in Wilmington, North Carolina. This is the precast yard, and you can see here the segment fabrication and storage in the yard. And so I want to start out by saying some of the previous segmental projects that I've been involved with and some of my coworkers have been involved with have been pretty large structures with hundreds of segments being precast. These 2 projects were pretty unique in that they were a very small number of segments. The Blue Ridge Parkway over I-26 had 62 superstructure segments and 14 substructure segments, and the Laurel Fork Bridge had 56 superstructure segments. So with that small number of segments, there's some unique challenges, and I'll discuss those later. But as Greg had mentioned, there's also an Aspire article in the spring of 2025 that I wrote that discusses some of those challenges of small projects and how standardizing shape can help make those more economical. And as we said, that is available for download in the under the handout section. So here are the project locations. Both of the bridges are located on the Blue Ridge Parkway in Western North Carolina. And the precast yard, Coastal Precast Systems, is located along the eastern coast of North Carolina. Some here, project stakeholders. You see there was a lot of overlap between these 2 projects. Cowie was the construction engineer for both. Structural Technologies was the PT contractor and erector for both of them. And then Coastal Precast had fabricated segments for both. And the bridges themselves were pretty similar structures. Each was a 3-span bridge with a variable depth superstructure, or superstructure. The span lengths were also similar. The I-26 project had a main span length of 275 feet. The Laurel Fork was slightly smaller at 235, but the end spans for both were 165 and 155 feet. So now I'm going to talk about the segment fabrication process. And the first step is fabrication of the rebar cage. And so that cage is assembled outside of the casting form in a rebar tying jig. This is one of the main items that leads to a faster casting cycle as opposed to like a cast in place where you're tying that rebar in the form. It takes us about 1 to 2 days to fabricate that rebar cage in the jig. And you can see here, because they were variable depth, we had to be able to adjust the size of that rebar jig. So here you can see a shorter segment being shown on the right. On the left here is one of the taller segments. And after that fabrication of the rebar cage is complete, that rebar cage will be lifted and moved over to the rebar ready rack. And in that rebar ready rack is when we would add slab bolster to the exterior faces and tie in any supplemental reinforcement that's not able to be installed in the jig. And then moving it out of the rebar jig also frees up that rebar jig to start tying the next rebar cage. And so then modifying the form in between each segment, because these were variable depth segments, the height had to be changed. And on the right here, that full bulkhead you can see, that height was changed by removing it and adding or adding or removing shims to raise and lower it. And then as well on the soffit table on the bottom, you have these leg pieces here that are varying height, and those were assembled in different combinations to get the different height that's required. And I want to make a quick note on the soffit tables here. So you can see 3 soffit tables shown, and it's important to have 3 sets of soffit tables for each casting form. When you're casting a segment, 2 of those are in use, 1 under the match cast and 1 under the wet cast. That 3rd segment is then able to be modified for the following segment, especially in the variable depth where you have to change the height and the width of the table. And then it also allows you to, after you remove the 2 previous segments, you don't have to immediately pick up and remove the segment, the match cast segment, off of the soffit form, as you have another one that's able to go into the form for the next segment. So the next step is coating the segment face, the match cast segment face, with bond breaker and rolling that back in. That rolls along rails along the bottom and rise on the manipulator to move it back and forth, and then you'd set that rebar cage into the form. Next, you're using a theodolite and auto level to position the match cast segment relative to the bulkhead, and you're adjusting that based off of the output of the geometry control program that's provided by the contractor specialty engineer. That program is run after each segment is cast with the as cast survey results, which will give you the setup for the next match cast. And that manipulator here on the right, on the bottom, that uses hydraulic rams to lift the segment. And as you lift that up, you're able to adjust the threaded legs on the bottom of the soffit table to adjust that height and position of the segment. And then another note here about some geometry control. So on expansion segments, there is a blockout, and that gets in the way a little bit of the typical geometry control points. So in red are the typical locations of those control points for your alignment and elevation. But you can see, in a segment like this where there is the blockout for the expansion joint, you don't have a spot to put those control points where they are set up in the program. So you have to move them back to a couple inches off of the new face, which is not actually at the segment joint now. And so usually you're not able to adjust that in the geometry control programs. Once you set an offset from the joint face, that's fixed for the entire cantilever or project. So you have to do a manual translation to get the new points when you're doing a setup. The next step is installing the core form. And again, to just speed up that casting cycle, you're doing all of your changing of the forms, adjusting the height, and adding in different anchor blocks while that is pulled outside of the form, so that you can install it and have a quicker setup time on the form when it's part of the casting cycle. Next, placing concrete. And so for our projects, we used both a pump truck and a concrete bucket that was lifted into place using a crane. To place concrete down into the center of the bottom slab, there's a little trapdoor hatch located on the bottom of the top form. I'll go back here a few slides. You can see it. You see it right in here. You see that little trapdoor that allows concrete to be placed down into the bottom slab as well as down through the webs. Here was an interesting situation that we ran into. While we were casting a segment for the I-26 project, our on-site batch plant broke down after 5 yards of concrete had been placed into the form. And we did not know how long it would take to fix the batch plant. We had, with the specifications, we had a set amount of time that was allowed between placement of consecutive lifts. And if we went over that time limit, it's a possibility that the segment could have been rejected. So we were trying to decide whether we should wait and place concrete after the batch plant was fixed, which may be over that 20 minutes, and if there's a cold joint, a probability of being rejected. So we decided to remove the concrete, and we decided to do that because it would have been difficult to remove this segment, leaving that 5 yards in there. The normal lifting points are located on the top of the segment, which has no concrete in this point, so it would have been difficult to lift and remove this rebar cage with the 5 yards of concrete in the bottom. And we also would have lost all of that reinforcement and had to reorder that, which could take a couple weeks to get that rebar that's specific to that segment. So we ended up removing the core form, moving the match cast back, opening the side forms, and we pressure washed and chipped out all of the concrete. And we were able to save all of that reinforcement. And we did replace the ducts in case they had gotten holes in during the concrete removal process. It took us about 8 hours to remove all of that concrete, but we were able to recast that segment using that same reinforcement cage 2 days later. There's a little video that should play of that. All right, next step is going to be that initial curing period. So we wrapped the entire casting form and match cast segment in tarps. This was especially helpful during the winters as this was an outdoor facility, so to control that curing temperature. And we did also have supplemental heat that was added in to maintain a nice good curing temperature. To ensure that we didn't get too hot or too cold, we had temperature probes that were placed in the concrete in the bottom slab and in the wingtips so that we could monitor that as the curing was happening. Next step is the aftercast survey. And so it's important that this takes place before removing forms or pulling the match cast segment out. You need to know the position of those two segments relative to each other without anything moving it. So that has to be done immediately after uncovering, but before removing any forms. And then after that, it's removing the segments out of the form. So you would collapse and remove the core form, open up the outer wing web forms. So that's these right here. You'll roll those back to create just a slight gap that you can see in here, just a couple inches is all that moves. But then you roll that segment out on the manipulator that we were seeing earlier on the rails. And then after that's rolled out, your crane will come in and pick it up. As you can see on the right here, we lifted the segments off of the soffit form using slings under the wings. We had to do it this way due to clearance issues with the crane that we had on site. We were able to use post-tensioning bars through holes in the top slab once it was out into our storage yard to move them around, and it took about 5 minutes to hook up the rigging with the post-tensioning bars, and it took about an hour to use the sling. So we definitely made sure after they were out of the form and off the soffit table, we used the post-tensioning bars to move them around. And then that pretty much finishes up the casting cycle, but then some other work that still has to be done to the segments, stressing and grouting of the transverse tendons. So we typically stress the transverse tendons while the segment was in the match cast position. There was a work platform available to us for easy access to hold the jack there. If we had to stress in the storage yard, it required using man lifts to move the equipment around and was a lot more time consuming. So we would stress those in the form, and then we would add in a corrosion inhibiting powder that we would blow into the tendons after stressing. And we did that so that we could minimize the number of grouting sessions required. Because of the small size of the transverse tendons, it only took about a half bag of grout to fill those tendons. But when you mix up the grout to pump it through the tendons, you go through 10 bags just filling up your holding tank and have enough grout that you're able to pump through the grout hose. So we didn't want to grout 1 or 2 segments at a time, wasting 10 bags to really only need 2 or 3 bags of grout. So we grouted segments in groups of about 10 to 15 to minimize the waste of grout. And then, as I said, on the I-26 project, there were also pier column segments that we precast, and that follows a very similar sequence. It's just casting vertically instead of horizontally. So in this case, again, the rebar cage is fabricated outside the form on a rebar jig, and then it's placed into the form on top of the match cast, as you can see on the right. Next, you're installing the exterior forms, and the post-tensioning hardware is installed and secured in place. And then we place concrete on these with the concrete bucket and with the crane. And then again, important to perform geometry control before you separate those segments so that you know their position relative to each other. There was a center line that was established on 3 of the faces, and you can see the white dots here. So we would survey that with a theodolite and make sure that we were maintaining a true vertical center line on these segments. And then on the right side here, you can see this is a column cap segment that is solid. Then the other segments below were hollow on the inside. This cap segment was being removed here, and you can see it's using the same lifting frame and rigging that is used on the superstructure segment to move them around. And that column cap segment was a mass concrete element. So we placed internal temperature sensors to maintain our temperatures, our differential between the center and the exterior, and also make sure that we did not increase that center temperature past 158 degrees. On the photo on the left here, you can see a pretty heavily reinforced cap segment. So then what are some of the benefits of using precast over a cast in place? I think the biggest benefit is the optimizing the construction schedule. So you're able to cast superstructure segments while the site work and substructure construction is happening. So that as soon as that substructure is finished, you're able to start erecting your superstructure segments. And the erection of the precast segments is faster than you would be able to do a cast in place. And then another benefit is the level of quality. So if you're using a PCI certified facility, you can ensure that there's a high level of quality control happening. They're regularly audited by PCI. And then you have some high performance concrete. So a precast pre-stressed facility regularly uses 9,000-10,000 PSI concrete on a regular basis. And so they're able to have a quality concrete that you're able to have good control over with the on-site batch plant. And so then benefits of using an existing precast facility, you have that land and storage space, as I was showing earlier. You have utilities that are already set up in place, as opposed to setting up a new casting facility. You have a batch plant located on site. Again, with high quality concrete that is regularly produced by the batch plant, you know you're getting high quality concrete. And then you also have existing equipment. So we have cranes already on site, mobile gantry cranes, boom cranes, and other equipment that you needed during fabrication process. However, there are some challenges of using an existing precast facility. The equipment. So while the equipment, already having it on site is an advantage, it also is a challenge in that equipment is on site because it's used for other projects. So in this case, you can see using that same crane to move around pre-stressed girders. So it takes a little bit of coordination to make sure that the equipment is available when you need it. It's not dedicated just to the segment process. And then I think the biggest challenge is probably the segment delivery. So as I was showing earlier, the projects were located in Western North Carolina. The casting yard is in Eastern North Carolina. So it was a challenge to get the segments to the project site, especially this being a landlocked project site, not on water. Our plant in Chesapeake had produced segments for the Bonner Bridge replacement, and that was over water, so they were able to ship them on barge. And with that, there's no height or weight restrictions, but you do have height weight problems when you're transporting by truck. So it was over 300 miles from the casting yard to the Laurel Fork project. And with that distance, it meant that one truck was only able to deliver every other day. So the first day, it was getting loaded and driving up there, and the second day unloading and coming back for another segment. So it required multiple trucks to be able to transport and keep up with the erection schedule. Here's a diagram of the truck that was used. Total length was 116.5 feet, 13 axles. And then some of the challenges were at one stretch with an 8.5% grade. They went about a maximum of 8 miles an hour up that grade. So it was a very long trip because of that. And then there were some narrow roads, narrow 2-lane roads. So that required blocking off both lanes of traffic. near the project site so that the trucks could deliver the segments. And then the heaviest segments were the I-26 abutment segments. Those were 94 tons, and they required a special trailer with additional axles as well. So the height is the big problem while delivering. Weight, you can add more axles, but you can only do so much to reduce the height. And as you can see here, for the I-26 pier segments, the total height was 21 feet from ground to the top segment. That was 16 feet of concrete, 2 feet of projecting rebar for the parapet, and 3 foot ground for the bottom of the segment to the ground for the trailer. And so that was more than the overpasses on the way to the bridge. We needed to get that down below 16 feet to make sure we could actually get the segments to the site. And so one of the ways we reduced the height was using coupler bars to replace projecting rebar. And when we cast the segments, we had the rebar assembled. That was due to just the fabrication tolerances of each bar. We wanted to make sure that they would easily be able to be assembled when they got out to the project. So we had them assembled, labeled them, and then took them apart before shipping, and they were individually labeled so they went back in the same spot and we knew that they would fit. But doing that still only got us down to 19 feet. We had, which is still too tall, so we had to do something else to make it to the project site. And for that, we decided to ship some of the taller segments on their side. The pier segments were only 5 feet wide, but 16 feet tall. So turning them on their side reduced the shipping height by 11 feet. And then for the typical segments, the tallest ones were 16 feet, but only 10 feet wide. So again, by turning them on their side, we're reducing that by 6 feet. So now that total height, we were at 13 feet, and we were actually able to get these under the overpasses after the project site. And we rotated the first 5 segments on each cantilever. We used a flipping frame to rotate them. You can see here the crane picks up the lower leg of that L and slowly rotates it. This flipping frame was used first used by Unistress on the Sarah Mildred Long Bridge. So our segments here in place on the flipper, we had to increase that vertical leg on the L so that our center of gravity right here remained below this rotation point. So as we're picking up from the left side here, we wanted to make sure that that rotation was controlled by the crane and not by gravity. So we didn't want that center of gravity to go past that rotation point and have that segment slam down. So we added a extension piece in the bottom here, which lowered the bottom of that segment and allowed that center of gravity to stay to the left side of that rotation point. And then once they were flipped, we lifted the segments using the temporary PT blocks that were used for erection. And we added in some beams along the top of our lifting frame that matched the slope of the web wall so that we were able to lift with the changing height of the segments and the varying location of the PT blocks. So here's some more pictures of that rigging that was used in the attachment to the PT blocks. And then, as I said, there's some challenges to casting small projects. The first is the learning curve. So it takes 1 to 2 times of casting each segment type to become familiar with the process and speed up that casting cycle time. And so as you can see here, the casting of the first and second pier segments for both projects was longer than the third and fourth time we cast those. The problem is with a small number of segments, we're already halfway through by the time we really start speeding up the casting cycle time. So you're not able to take advantage of that knowledge that you learn each time. By the time you get it, you're done casting the segments. And then another challenge is only using one casting form for your pier segments, for your expansion abutment segments, and your variable depth typical segments. So on a larger project that I was involved with, we had 3 different types of forms. There was one form that worked exclusively for pier segments, one form that cast the abutment segments and constant depth segments, and then a form that cast the variable depth segments. But because a small number of segments, we had to have one form that would do all 3. And so we had the pier segment forms. This utilized 2 bulkheads, and there was an insert that would go inside the typical bulkhead. You can see here to form that diaphragm of pier segment. After the first segment was cast, the first pier segment was cast, it was pulled out of the form, spun around to use the split pier face over here to cast the next pier segment. And then when casting the abutment segment, we had another bulkhead as well, a different configuration. But the biggest challenge here is removing the top of the wing form. Now with that expansion block out, it's a thicker top slab. And so the top of the form had to be removed there. And then our typical segment forms, you see, you don't have that diaphragm in there, so you have your core form that forms the inside. And then because we used one form for the entire project for the different segment types, that led to longer casting cycles. Our casting cycle time was about 2 to 3 times longer than average. We were casting at most 2 segments a week. And that was, again, just due to the complications with the form of having the different setups that it needed. So because it took a lot longer on the casting cycle time, we had to begin casting far in advance of the erection. They were erecting up to 8 segments in a week. And well, like I said, we were casting a maximum of 2 segments. So we needed to have a majority of segments cast before erection started so that there wouldn't be a delay in erection. Now for the Laurel Fork project, we actually did fabricate a second form that was used to cast the abutment segments. This saved about 3 weeks in the schedule for form changeover. Unfortunately, this form was only able to cast the 2 abutment segments. It utilized 2 bulkheads. You weren't able to cast against a match cast segment and adjust for geometry, so it was only usable for those 2 segments. But besides those 2 segments on the Laurel Fork project, segments for both projects were cast in the same casting form, as you can see here. And obviously it's good to get that extra usage out of the form, since it only cast 62 segments on the first project. It still had a lot of life in the form. The only issue was that the segments were not the same shape or size. So here you can see an overlay of the 2 different segment shapes. The I-26 project was a taller and wider box than the Laurel Fork. And there was some differences in that section as well. The rounded top corners here and the haunch and the bottom slab were different. And we were able to work with the contractor's engineer, Cowie, to modify the shape on Laurel Fork to more closely resemble the I-26 project. So as you can see here, we eliminated the radius in the top, eliminated the haunch, and we also reduced the thickness of the top slab from 10¼ inch to 9 inches to match the I-26 project. So that definitely helped speed up the form change time, although it did still take us about 4 to 5 months to do the form modifications required from the first project to the second project. So one of the things we had to do, as I said, the Laurel Fork, it was narrower, almost 3 feet narrower. And so we had to move in the web walls. And so we did that by removing the form. We added in some beams on top of the existing structure. And then we replaced the forms on top of that to move those in to narrow that shape. And then we also, as that shape narrowed, the bulkhead narrowed. And so we had to move in the mounting locations of the bulkhead. So we added on extensions to narrow that bulkhead down. And finally, the core form had to be narrowed. And to do that, we kept all of the structure and the rails down below the same width, and we just decreased the width of the segment that actually goes inside through the bulkhead to form the core. And the different wing shape was accomplished by adding on form on top of the existing form. And so one of the things that was a challenge in converting from the first project to the second was the different segment heights. So the joint heights were different between the two. And so when forming the core form, there's a certain combination of segment pieces that had to be used to form the height required. And so now it was not the same heights required. And so we didn't have any existing plan or drawings that showed which pieces need to be put together in what order to get the form. So we kind of had to go through and try it out. We did sketch it beforehand on the computer, but it did require certain trial and error to get the correct combination of forms in there to get the height correct. And then I just wanted to go next into some thoughts on segment design and detailing from a precaster's perspective. So I had started my career at an engineering firm doing some design and detailing of precast segments. And after about a year there, I was sent to a segment fabrication yard. The idea being that seeing the segments actually assembled would help me become a better engineer and detail better. And I think it did. I saw a lot of things that I had done on the detailing side when put into actual practice and use that did not work out so well. Especially the detailing things down to a 1/16 of an 1/8 inch so that it would fit, did not work so well with fabrication tolerances. And so I saw a lot of the challenges of trying to assemble things when you detail it to such detail. So one of the things I wanted to look at that I had learned was some of the bottom slab anchor blocks that I had detailed. So in this case, you can see the reinforcement here of the anchor block where it projects down into the bottom slab. To avoid the tendons in the bottom slab, I had made 3 different size anchor blocks. As you can see, that reinforcement that is along the face right here of the block, that's shown in red. So that was adjusted to avoid conflict with the tendons. However, a smarter decision that I realized later would have been to make them all one size, and instead of having that main reinforcement always be at the face of the block, I could actually have it jump inside some of the tendons as you see here with the dots, and then add supplemental reinforcement along the face. As you see, this was done on the Laurel Fork project. Another thing that I think is very helpful is using spliced web wall reinforcement. So this especially comes into play during variable depth segments, where if you detail a full length bar, you're now using maybe 15 different bar callouts along there to get the height correct in a series. Or in this case, you can detail to the tallest side and just make sure you have your minimum splice length. And then as you decrease along the length of the segment, you would just have a longer splice length. And so that makes it easier also for fabrication tolerances then, if there's that adjustment available in the field. And then there's also rebar congestion comes into play. So it's one of the things I think is very important is to detail your reinforcement, the actual width of it, and not just as a line, which help you see some of the conflict. This is on the right here is a picture of a deviator segment, and a lot of conflict comes into play where the web reinforcement overlaps with the 90-degree hooks from the bottom slab. And you see a lot of reinforcement in that area, and there's not a lot of concrete that can get in there. And one thing we were actually able to do because of that spliced reinforcement in the web we actually had a longer splice length than required. And so we were able to trim some of the tails you can see in black here. Those were all bars that were able to be trimmed to avoid some of that overlap. Next thing that I've seen is floating reinforcement and PT ducts. So in this case, the height of the transverse post tensioning did not line up with the reinforcement in the top slab. So it's very convenient to be able to tie the ducts directly to the mat. In this case, we were not able to tie the PT ducts directly to the top mat. We had to tie up and down and kind of hold them floating in space between the mats. There was a 3/4 inch gap from the top of the post tensioning duct to the top slab, and then also a 3/4 inch gap in the center from where it was at its low point to the reinforcing mat. And then, so I wanted to talk about how forms are stripped and when, the way that the core form specifically, and how some detailing of things can become tricky there. So to remove the core form, the common steps will be to first remove the bracing along the bottom, and then you would use these hydraulics to retract that core form towards the center. And you want to hopefully retract enough to avoid removing this form in the upper corner, your temporary PT blocks. But then if you still need more, you can also rotate around here and lift these bottom sections up. So this was a project where the blisters on the bottom were not conducive to stripping the form towards the center line. You can see you have a larger concrete piece right here. So this form that will be placed in here doesn't allow you to just strip those towards the center. You actually have to unbolt the form. As you can see over on the right here, that piece had to be unbolted and left behind and removed at a later date. Another issue that I've seen a few times is when lifting, the location of the cantilever tendon blockouts when lifting the segments. So as I was saying before, we used slings placed at the base of the cantilevered wing to lift the segments. So as you can see here, well, there are certain segments that have the cantilever tendon anchoring directly over that location, and you have that thin section of concrete below, and that's right where your slings are going to be bearing. So we did try to add some tube steel here to get the sling off of that corner. Ultimately, it did not work, and this was after we removed the sling. When we set the segment down, it had busted that off. That happened to multiple segments, and I've seen that on multiple projects as well, where that same issue occurs. And then here is the segment where it's being removed from the form. As I said, the wings out here move only a couple inches. They rotate down. You see that small gap here as that segment's being removed. So one of the things that is difficult is when you have items projecting out of the segment. So in this case, that scupper projects down through into the top of the form. And having that in place, we would not be able to roll that segment out along the rails. So we ended up doing a secondary pour to cast that scupper. And another way I've seen that handled is using an embedded plate here, which you would then take and bolt a flanged drain pipe below, and that's so that you don't have anything projecting into the form when you're casting. And then I think another really important item is the communication. So early and often communication. As I mentioned, especially with a small project like this, we started fabricating the segments well in advance of erection. That also meant we were fabricating while there was still some changes occurring to the design and to the shop drawings for erection procedures. And so one of those changes that happened was the base segment for I-26 was reduced in height to allow for a larger cast in place section where they could connect the ducts in the footing to the bottom of the column segments. Unfortunately, that change was already after forms were fabricated and on site. So we ended up having to construct this base section to reduce the height of that base segment. So sooner communication would allow those changes to be implemented in the formwork design and fabrication. All right, and that's all I have. So I can take any questions, and thank you.
Okay, great. Thank you, Jacob. Interesting presentation. It's always fun to see these details from the precaster's point of view. It's oftentimes as designers, we don't really think about some of those things. We've got several questions here. Wanted to start here with this one. How do you control the geometry of the rebar cage as it's being assembled?
Yes, so I'm wondering if you're talking about like the curve, the horizontal curve that may be on there. So for our segments, we did have a different length longitudinal bars for each side on each side of center line. But then we also did have to, once that cage is set in the form, we would have to make adjustments, especially to the height of the web wall reinforcement. We would take a level from the bulkhead to the match cast segment and adjust that splice length on the web wall bars to make sure that we had our top slab clearance. So there is some adjustment that has to happen once it gets into the form.
Okay, great. Was the post-tensioning and grouting performed by you guys in-house, or did you have a third-party subcontractor doing that work?
We performed that in-house for both projects. I am ASBI and PTI grouting certified, and we had a couple other people on our staff that were as well. So we performed that. The grouting equipment was sent to us by the post-tensioning supplier, Structural Technologies, but we performed the actual grouting and stressing ourselves.
All right, good. What was the physical hardware that you used for the geometry control points in the segment decks, the elevation control and the centerline control?
Yeah, so in the top deck, we placed plastic bolts for the elevation control. So 4 of those in a segment. And then we placed pins, hairpins. We bent stainless steel wire. I don't remember the size, but thin stainless steel wire. We bent that into like a horseshoe shape and then placed that in the top for the center line.
And were these segments cast with the final riding surface, the as cast top surface, or was there an overlay on these bridges?
Yes, so there was an overlay. Yes, there was an overlay for both of these segments. On the Laurel Fork, I believe it was an asphalt overlay, and I believe it was a concrete overlay placed on the I-26 project. I could have that backwards. There were 2 different overlays that were placed. Both did have an overlay.
Okay. Do you know if the geometry control hardware was removed after the segments were erected?
I'm not sure on that.
Yeah. Okay.
I'm not sure.
Okay. You talked a little bit about rebar fabrication tolerances, especially with regards to the variable depth webs for the typical segments. How did you handle rebar fabrication tolerances for the pier and abutment segments?
Yeah, so that was also difficult. Kind of the best we can. Not all of those were the 2-piece bars then. So we ordered more than what was required. If the segment needed 20 bars of a certain size, we'd order a couple extra. So if there were any that were a little bit too tall or too short that encountered a problem with then placing of the post tensioning, we were able to replace that bar.
Okay. Did you guys have any trouble with getting good concrete consolidation in the deviator blocks during casting?
Not really, no. we had form vibrators that we used and internal vibration. Those deviator blocks were detailed pretty well, that there was access from the top, and there was also in the form there were windows that we were able to open to place internal vibrators through to vibrate the lower sections and then close as we filled them up. We did have a few segments that had some small honeycombs in the webs, and we were able to repair those.
Do you feel like that happened earlier in the process? Was that part of the learning curve?
Yeah, a little bit was the learning curve, definitely, and how much vibration is needed depending on the concrete. I'll say it was the slump limits on some of the concrete also came into play. The higher slump, the better workability it is for us. So we always like using higher slump concrete. So yeah, the allowing higher slump concrete makes it easier to get that consolidation.
During cold weather, did you have to do any preheating of your match cast segment before placing concrete for the wet cast segment?
We did not, no. We did not do any preheating before casting. We wrapped everything in blankets beforehand, but we didn't actually start adding that heat until after the concrete had been placed.
Okay. So I know from personal experience that the National Park Service, who owns these bridges, has some pretty strict aesthetic standards that they like to follow. Did you have any contractual requirements or procedures that you used for maintaining a consistent concrete color for each segment on these projects?
Yeah. So we did rub each segment, the interior, to fill all bug holes and get a consistent finish. Also on the exterior, if there was anything that not matching color-wise or bug holes, we did rub the exterior as well. We had placed also a clear curing compound on the exterior. I don't know if you saw during the presentation, some of the segments look pink on the outside. That was a clear curing compound with dye. So that was also placed, and that pink color would fade away over time. So yeah, rubbing the segment was one of the biggest things that we had to do to get the aesthetics.
Okay. What was the typical casting cycle time for the precast column segments?
For the column segments, we were casting about 1 to 2 of those a week. So 3 to 5 days was the casting cycle time on those.
Okay, so they weren't quite as quick as the superstructure segments.
Correct. Yeah, they're. I guess going into it, I thought the column segments would be easier to cast. I would say those are actually a little bit more tricky than superstructure segments to cast. The geometry control can get kind of tricky on those.
And did you cast out all your precast column segments before you started casting superstructure segments because of the erection schedule, or were you casting both kind of at the same time?
So due to the formwork lead time, we had gotten these substructure forms first and started casting. But during casting of the substructure, the superstructure forms arrived, and so there was a little bit of overlap. We intentionally had the substructure forms come in first so we could start, but once the superstructure forms got there, we were casting both at the same time.
Yeah, that makes sense because you can erect those precast segmental piers fairly quickly, so you wouldn't really have a lot of lead time before you needed your first pier segments to get erected.
Yes.
So,
yeah.
Who fabricated your superstructure segment forms?
That was fabricated by FCO.
FCO, okay. And do you think that you'll keep them at your site there for a while in case of possible future projects?
So that's a great question. We still have the forms. We have disassembled them. One of the problems, and I kind of talk about this in my article, in the Aspire article, is just the difference in shape of segmental projects. You typically don't see a repeat of the shape. And so it's even these two, with Cowie helping, make them more similar, there was still enough differences that there was a lot of damage done to the forms at reworking them, where it would be difficult to use them again. And now, because we did modification in-house to them, we don't have the assembly drawings that we had to start with. So it will be very difficult to reuse those forms. We still have them, but we don't anticipate being able to use them again.
So kind of along those same lines, did you win the contract to cast the Laurel Fork segments before you were done casting segments for the I-26 bridge? Or did you keep the forms in anticipation of bidding that work in the future?
So we knew that we were going to be reusing that. We had the Laurel Fork project had already been awarded while casting of the I-26 project was still going on, and segments were being delivered for that. We did hold off on form modifications until the last of the I-26 segments were delivered, in case there was an issue during delivery or transportation where a segment was damaged and needed to be recast. We didn't want to tear apart the forms and not be able to recast a segment if it was needed.
Yeah, that's a great point. I'm glad you mentioned that. That is something that we always need to consider.
Yeah.
Hanging on to at least one typical set of segment forms would be, pretty smart. That's good. You showed U-shaped barrier rebar that then had couplers for each of the legs of the U. What type of couplers did you use for those?
They were Lenton, I believe. They were positional couplers. So the top bar, that top U bar, was threaded double the length required. So you would spin the coupler up completely onto that top bar on both sides and be able to lift it up. And then when you went to install it again, that coupler will be fully threaded up into the top bar. You'd place it over the bottom and spin it halfway down to connect on the lower embedded bars. If that makes sense. It might be hard to describe and get a visual on, I guess.
No, that's good. I appreciate that. When you tilted your segments onto their sides, was there a concern about tensile stresses in the bottom of the wings from the transverse PT that had already been stressed?
Yeah, so that actually was analyzed. Cowie had done analysis on the tilting of the segments to make sure that there were no adverse effects, since obviously during design you're not thinking about it on its side and how that will create different stresses. So yeah, that was analyzed.
Okay. Back to the curing compound stuff a little bit. Was the curing compound part of the project specs, or what was specified for curing in the contract documents?
Yep, it was specified to cure all visible sections. So the interior of the box, the outside with a clear curing compound, and the deck was had a white curing compound, and then that was later ground off before the topping was placed, the overlay was placed. So that was specified. Yep.
All right, and here's just to kind of finish this off here, here's a big picture question for you. What can be done by precasters, contractors, and designers to lessen the learning curve on segment fabrication?
I think standards are a big one. So we're a precast pre-stressed facility, and we produce a lot of pre-stressed girders. Those are fairly standardized. So we, jumping from one project to the next, there's not really that learning curve. The forms are the same shape, so the concrete piece is the same. The reinforcement layout is very similar. So it's the standardization as much as possible really helps reduce that learning curve. And then with that, I would say a big learning curve is in how the forms work and how you have to use different form pieces. So again, that goes to if you can keep a standard shape as much as possible between projects, you would be able to reuse that same form and not have to learn a new forming system over again.
Yeah, no, that's good. And maybe not only standard shapes, but also like standard details for blisters and PT anchors and things like that too, right?
Yeah, absolutely.
Yeah. Okay, fantastic. Well, I think we're just about out of time, so that's going to wrap up our questions for today. Jacob, thank you once again for a great presentation. And with that, I will turn it back over to Greg.
All right. Well, thank you, Jacob. Great presentation, and appreciate your insight today. Certainly a unique perspective, like I said, for us to have a precaster for a change. And then just one more little plug. Again, thank you for attending today. If you have questions or comments about this session, there's an email address there on screen. And again, encourage you to follow the American Segmental Bridge Institute on LinkedIn. If you haven't already done the registration for our 2025 webinars, again, here's the QR code or a SurveyMonkey link if you like to type URLs. But you can use the QR code or go to our website. You will get, or you should get then, an email about the June webinar here in just a day or so. So you can get that on your calendar. So with that, we'll go ahead and sign off. And again, thank you everybody for attending today, and take care.